Thank you for watching my popular science presentation. This presentation is my attempt at distilling and communicating my PhD research on local learning algorithms for emerging hardware in an accessible manner. Motivation for my research project comes from biology and neuroscience, where it is well known that biological neural networks are very different from the artificial neural networks employed today. The brain both involves rapid feed-forward processing driven by sensory input, but it also involves feedback and general recurrent connectivity, which is believed to be responsible for higher level cognition, memory, and attention. Today, recurrence is somewhat underexplored, and when it is employed in artificial neural networks, it is trained in a way that requires you to backtrack through the temporal dynamics of your network. This is memory costly on digital hardware, and on analog hardware it is outright impossible. My research has focused on developing ways to train such recurrently connected networks without needing to unfold the temporal dynamics. To motivate why we should care about analog computing today, I'll give a very brief history of computing. Early computers were analog, meaning their states could take a smooth range of values. Having continuous states, analog computers are non-deterministic, meaning running the same program twice results in slightly different outcomes each time. These devices were hardwired to solve specific problems, and solving a new problem would mean physically rewiring the machine. Digital computers have discrete states. This is part of the reason why they can implement deterministic programs. With the advent of stored programs, it became possible to run many different programs on the same machine without physically altering them, making them much more useful. In more recent times, we've seen the development of a variety of specialized digital computing architectures in which many processors divide the work between each other. This is, for instance, useful in neural networks where you deal with lots of linear algebra operations, which can be very neatly divided among these processors. A downside is that such devices are very, very energy hungry. So what comes next? Actually, AI doesn't necessarily need discrete states or deterministic operations. Furthermore, analog hardware, which lacks these features, tend to be much more energy efficient. However, a pressing question is what kind of algorithms we would use to train analog AI systems. And this is what I have been researching. Before talking about how neural networks can be trained on analog hardware, I will show you a little cartoon of how it is done in digital hardware. Typically, you use an algorithm called backpropagation of error, in which you inject some input data, for instance, an image of a dog, and then you map that to a new layer via a set of learned parameters, weights, that's the blue arrows here, and you keep doing that across the layers at each single time step. Once you reach the output layer, your network makes a prediction, which is more or less wrong. And then based on how wrong it is, you can backpropagate this error signal using analytical expressions for how each parameter depends on each other. And this allows you to propagate this error signal all the way through your network, telling you how you should adjust the parameters. In analog circuits, on the other hand, we don't have a global clock, so we can't have the same fine-grained synchronization as we had in the digital case. Rather, neural states evolve continuously, and error and activity signals flow in both directions simultaneously. Network predictions are found by letting the network relax to an equilibrium state. That is a state that minimizes some scalar function, typically called the energy function of the network. And And you can choose your hardware such that this is something that happens spontaneously in very short time. One way to train such a recurrently connected network is to infer the states of the network twice, subject to different boundary conditions. That means we would inject some, first we would inject some data into the network, for instance a picture of a dog, while also telling the output neuron that this is a dog. And then we would let the white neurons relax to equilibrium, and once we're at equilibrium we would adjust the weights in order to make this configuration of neuron states more likely in the future. The next thing we would do would be to try to unlearn bad associations. This can be done by not showing the answer, and then let all of these white neurons, which now include the output neuron, relax to equilibrium. And once we're at equilibrium, we adjust the weights in a way that makes this configuration less likely in the future. The main focus of my research has been to derive contrastive learning algorithms like the one on the previous slide by formulating neural network training as constraint optimization problems. Depending on the constraints you impose on the neural dynamics, you get algorithms with very different properties. You can, for instance, get neuron and weight updates that are local in both space and time, which is often desirable for analog hardware. You can also choose constraints such that your network exhibits more biologically plausible asymmetric connectivity, or you can choose constraints that make your neural network more robust to perturbations, which is highly relevant on noisy analog hardware. So, will analog AI be a thing in the future? It's hard to say, but my guess would be that we will see a much more diverse compute landscape in the future, and that the analog hardware and analog-friendly learning algorithms will find a niche in cases where energy efficiency is important, somewhere in this landscape. Thank you for taking the time to listen to my popular science presentation. I hope it made you curious about alternative learning algorithms and computing.